Hello. Today we will be looking yet again at an example of Newton's second law, and that is motion with non-zero net force. In this video, we will be observing the motion of a paper ball as it is dropped from a certain height. Here the problem is to create a computational model that predicts the motion of the falling object under a non-zero net force. This will involve analyzation of the video of the ball using Tracker and plugging in data obtained from Tracker into Vpython. Two predictions from Vpython will be made. One where the net force is just equal to the weight force, and one where the net force is equal to the combination of the weight force and drag. The result was that the model that also accounted for drag best modeled the actual observed results. Let's look at how we arrived at this conclusion. First and foremost, let's take a look at the physics involved. We'll be using two forms of Newton's second law, which you can see on the screen now. The first one being especially important as it deals with net force. The next two formulas were used to calculate the net force acting on the ball. We will talk about how we calculated the constant b on the drag force equation a little later. Now we will take a look at the observed motion of the object. As I play the video, we can see the ball moving along the negative y-axis because the axes have been flipped about 90 degrees to the left to account for the flipped video. As we can see to the right, the graph is not linear, so we can see that there is a change in velocity. Referring back to Newton's second law, because there is a visible acceleration and mass is not changing, there is a net force on the object. Now we can enter Vpython to predict this movement. Here are the initializations for the model prediction where the net force is equal to the weight force compared to when the net force also accounts for drag. Here the initialization is the same for both predictions. The ball mass is equal to 2.8 grams. The ball position is a vector of zeros, and the ball velocity is also a vector of zeros because we assume the ball starts from the origin and at rest. Here for the two predicted models, the first being the weight force is equal to the net force, we have a delta t of 0.003, which is a small time step compared to the total time of 0.6 seconds. We have a gravity force of 9.8 and a j-hat vector of 1 in the y direction to tell which direction the ball is moving. Then we have the net force is equal to weight force plus drag force. And the only thing different here is we have a b constant, which was calculated by plugging it into the drag force equation and seeing where that model prediction had its final velocity equal to that, or final position equal to that of the observed. Now we look at the while loop calculations. For the net force equal to the weight force, we have the weight force is equal to the negative ball mass times g times j hat, which is the same as saying the ball mass times g, and j hat indicating the direction in which it's moving. For the second prediction, the only difference is that we added in a drag force, which is equal to the negative b, which I just told you how to calculate earlier, times the magnitude of the ball velocity squared. And the F net here is equal to the weight force plus the drag force. Looking at the graph motion for the observed and the two cases for the net force, we can observe a couple of things. First, when comparing the modeled without drag, which is the light pink graph, we can see that it predicts the ball moves farther in time in the time interval than does the observed. This hints that another force could be acting on the ball to cause it to move a shorter distance. When we factor in a drag force, the slope of the curve more accurately represents that of the observed. Although the model accounting for drag has the best fit, it is still not perfect. Around the middle, the model seems to underpredict the distance that the paper ball fell. This might have been due to the fact that the paper ball probably did not start exactly at zero velocity, or the fact that the ball was blurred, so the estimate of the point mass was made at the center of the blur in Tracker. Overall, though, this model fairly accurately represents the motion of the ball. Now let's look at the discussion questions. The first question being, do any of the models predict the terminal velocity? In this case, yes, the model that accounts for the drag force would predict the terminal velocity. When the object reaches a terminal velocity, the net force on the object is 0, and so is the change in velocity. For the net force equal to 0, the drag force has to be equal and opposite to that of the weight force. The second question is, does the initial velocity affect the terminal velocity? The answer to that is no. The terminal velocity is independent of the initial velocity. The only thing initial velocity would change would be how fast that object reaches terminal velocity. And in order to help explain this, I have included force arrows in my code, including both gravity and drag. You see that the gravity force in yellow is constant, while the drag force gets larger as the ball is accelerating. So as the ball velocity reaches a certain point, the drag force arrow will be equal to that of the gravity force arrow, and the ball will have reached terminal velocity. In conclusion, we can see that an object falling does not fall at a constant speed unless it has reached its terminal velocity. In regards to this lab, the object has a net force acting upon it and is modeled well by the prediction considering both the weight force and drag.